All right, coming in next, we have Gaia with Facebook. While he's working his way up, I want to take a minute to recognize our fellowship recipients. May or may not be in the room right now, but I'll ask they stand and give us a quick wave. We have Bronwyn Lewis was a recipient this time in the room. No? All right. Aaron Rusinski and Colin McIntosh, our three fellowship recipients this cycle. So thank you very much for all those that applied, and congratulations, folks. Here we have Gaia with Facebook. Gaia.
Thank you. Hi, my name is Gaia, and I'll be talking a little bit about Facebook Backbone. Before we start talking protocols and topologies and all of that stuff, let's take a look at the raw numbers and the scale that we deal with. You know, Facebook is pretty global. It has like 1.28 plus billion users, and it's growing. You know, over the last couple of years, we saw a major trend change. We saw a lot of our users move into the mobile space. Right now, it's sitting at about 600 plus million users. What does this mean? This means the fact that now we are catering to a section of users that are at variable bandwidth and varied latencies or increased latencies as well. This also means like the traffic patterns inside the backbone change with the shift to mobile. In addition to the changes that happen outside of Facebook's realm, we also have things that happen within our domain itself. Currently, we have Instagram that's sitting at about 200 plus million users. One of the other things, how many of you loved the 1 minute look back that we did for the 10-year anniversary? It's pretty awesome, right? Let me tell you an interesting story about it. All of that was conceived and executed in about 2 to 3 weeks before the launch. Think about it. We have 1.28 plus billion users, 1 minute look back done in 3 weeks. All I'm trying to say is that what it means to us as network and infrastructure is the fact that not only do we need to be reactive, but we also need to be proactive such that we are able to make these business services and products get rolled out. On that note, let's get back to the basics and look at our topology. So we run a pretty traditional backbone. So we have a bunch of clusters that sit in data centers. They all connect to this data center router layer. This is our label edge router. This is where our imposition happens. This is the gateway for all the machines out of the data center. And we have a standard backbone layer. We run a true BGP-free core. This is labeled switch router in our network. The other end of the paradigm is the edge. Here's where what we call our peering routers, or PRs. These get us basically our external connectivity to the users. All of them, among the edge routers, run a bunch of MPLS LSP meshes. A quick rundown of our protocols. We like to keep it simple. ISIS used for us our IGP, IBGP and eBGP for our peering, RSVP signaling, mainly because we use FRR and sub 50 milliseconds failover. And we also run out of bandwidth. It's a self-healing network. We have a lot of flows. They're bursty. It helps like being adaptive. Let's quickly take a look at the pattern in our backbone itself. So if you look at this, the graph that's being shown, there's a significantly large proportion of machine-to-machine traffic. As we start rolling more services out, as our data centers is starting to grow, we find the chatter among these machine-to-machine services becoming more and more. Not only that, it's an interesting traffic packet size pattern as well, according to us. Let's look at the packet distribution at the edge. This is a pretty standard iMix pattern. We have about 35% of 64-byte packets. The average packet size itself is about 810 bytes. Let's flip the coin, and let's look at what happens at our DR, data center routers. Here's where it gets interesting. You see a large amount of small-sized packets. So we have about 60% of 64-byte packets. And now the average size becomes less than 300 bytes. So now that we've discussed this, let's look at some of the challenges that we face with the backbone itself. I think a lot of people in the audience know this graph. The demand continues to grow. What happens with this is capacity planning becomes a big challenge for us. The other well-documented challenge with a TE-based auto bandwidth-based backbone is binpacking. Third one that we significantly face is scheduling. Currently, we have millions and millions of flows, and the current paradigm of protocols does not allow any kind of scheduling among them. Let's look at what capacity planning challenge is. So this is kind of the graph that comes out, right, in general in a network. Why is it this way? So we try to protect all the bits that go across our backbone. We also capacity plan our backbone for worst case failure analysis. What does that mean? We make sure that it survives a single node failure or a single link failure. We have utilization that basically has regional peaks and global peaks and so on. So we'll have a bunch of valleys, but ultimately we also have an over-provisioned backbone. The other aspect that I touched upon earlier was binpacking. A lot of our services have certain latency thresholds that we want to honor. So ideally, we would like to run our links pretty hot. We want to run our shortest path as hot as possible. Let's take a look at how it breaks in the current paradigm. So let's say we have a demand that goes from A to C. So we build an LSP that is at around 3 gig. Let's assume that all of the links are at 10 gig bandwidth. A few minutes happens. A few minutes later, a second LSP comes in, which is now catering to the demand that goes between node E to node C. It is still at 3 gig. So currently 6 gig is utilized among the 10 gig link. Few more minutes happens, the demand between LSP A to LSP C increases to 6 gig. Auto bandwidth kicks in, reoptimization happens. This is perfect, right? We are utilizing our 10 gig link at 9 gig, which is great. Here is where it breaks. The next time, the demand between E and C grows to 6 gig as well. Now we cannot have 12 gigs in the 10 gig link, so we have to break the shortest path and we move away, which is fine. But unfortunately, there is no mechanism today that can break the subflow, the flow between E and C, into 2 flows and actually make sure that we utilize the link B to C to maximum. Right now, we have about 4 gig of traffic or bandwidth that's available on B to C that's not utilized. The other aspect that we talked about was scheduling. The only way we can alleviate the problem currently is by using QoS. So we have 3 classes of services. AF4 being premium, followed by AF2 and BE. It's the only way that anything can happen in terms of guaranteeing SLAs if there is capacity constraint. There is no way of doing kind of application to understand what's happening in the network and backing off. So we talked a little bit about the problems. Let's see solutions. If you have seen the video about Facebook Campus, or if you walked around Facebook Campus, we are a big believer in slogans. And in the recent F8 conference, Zuck jokingly put this up. He said we are going to go to a move fast with stable infra. This does not mean that we are going to suddenly introduce change reviews and multiple levels of peer reviewing and so on. If you listen to our David Swafford's talk at Nanog in Phoenix, you would have known that we believe a lot in automation. And over the past few months, given the size of our team, this has basically enhanced our view. What this slogan means to us is we got to be intelligent in building our systems. We got to automate. We got to be able to build systems that can be reused by other decisions that can happen to make our network more programmable. So the first such system that we built was what we called Network Global View. For anybody who runs a backbone that's big, which is a mix of peering circuits, which is a mix of transport lease circuits, which is a mix of transport-owned circuits, a single source of truth or a desired view of the network is very, very important. A lot of times we sit and we have a maintenance and people ask us, hey, can we take down the shelf? There's always a prayer that goes on, hey, I hope my shared risk link groups are right. I hope nothing has changed. So that desired view was very important to us. So the first thing we did was we built something known as CircuitDB. What it did was it basically took a holistic view of all of our network, all of the links that we can use, all of the shared risk link groups that we have. So we could actually do some resiliency analysis offline. We automated it. We made it repeatable. This gave us an ability to also audit things. We have a desired view of the network that we think, and we have a derived thing that actually we get from polling and monitoring and so on. And finally, this gave us the visibility. This was the system that we could point maybe our edge fabric design or edge intelligence that we want to do, or the backbone, more like the TE controller or TE decision engine that we want to do. We could point it to this system. So we built this system, and then how do we make sure this stays the way? This basically stays like the single source of truth. This has the data integrity. So the best side effect that we had was like, we could get into this automated provisioning, automated decom, automated groups, everything. So we ensured that a manual person does not go and touch the router. It's all done through this tool. So what happens? Let's say we are going to go ahead and we are going to provision a circuit. It could be coming in from an optical system. It could be coming in from peering and so on. The first few things people do are essentially like, port map planning, reserving ports, circuit testing. Once this is completed, what happens? You go, you allocate an IP, you do a config generation, and you push it to the routers. What the system did was did all of it in an automated manner. So that essentially ensured that our single source of truth that we built continues to be the single source of truth. I had alluded earlier about our demand growth, right? Let me tell you a story about what happened when I was sitting like in a couple of capacity planning meetings. So we launched Graph Search last year. So we were sitting in a meeting, and people are coming to us and saying that, hey, we need to transfer our Graph Search indexes across coasts, across continents among the data centers. We're like, OK, that's pretty cool. What is the amount of data that you're transferring? It's petabytes. We're like, wow. So we said next week happens, and then Hadoop wants to do a namespace move. So all of this basically translates into petabytes and terabytes of data that needs to be transferred. So quickly we came to a realization that what we needed was a holistic view of all the jobs in our system as well. So that kind of led to what we call the traffic manager, or like a bulk traffic manager control. So typically what happens in our network is, so we have a source tier, which is a collection of hosts that's sitting in a data center that basically wants to transfer traffic, some X amount of data, to a bunch of destination tier, as we call it, which either may sit in the same data center or it sits across the backbone. So the first thing we did was we said, hey, we need to actually have a lightweight daemon that can actually sit on every host in our data centers. This, basically the daemon, will then talk to what we call the bulk TM aggregator. The aggregator essentially is a collection of all the jobs that need to happen. So let's say we have Graph Search that comes in and says, hey, I need to transfer X amount of data. Or Hadoop comes in and says, I need to transfer X amount of data. So they all talk to this global aggregator. Now this job manager or the global aggregator will in turn talk to a backbone path computation element or a backbone controller, which we'll talk a little later. So all the bulk traffic manager gets is essentially a transfer rate, which then it goes ahead and programs it on all the hosts. So let's say a job has some amount of minimum bandwidth that it can take and transfer these jobs. So what we also did was basically using IP tables and IP rule set and Linux TC shaping function, we ensured that we could actually monitor them as well. So let's say we have a source tier that is requesting X amount of bandwidth, and it's like given about 100 Mbps. But it's not transferring 100 Mbps. So we can actually take that bandwidth away and give it to some other job. And since we are continuously monitoring these, as soon as we find this tier actually starting to transmit more traffic, we bring it back to the assured minimum bandwidth level. So this was kind of like, gave us a view of the entire jobs that we want to, what are the applications doing? And then we can actually start talking about controlling them. So now that we had a view of the network, we had a view of all of our jobs. The next logical thing was to actually do something known as path computation element. Basically now, let's run an algorithm. Let's make sure all the demands that we have can be placed optimally in the network. So what's the current paradigm? We basically have a distributed system. We have every router doing what it thinks happens best in the network. Let's take it away. Let's now remove it, and we have this centralized element that can actually look at everything. So we have all of the statistics that we need. We have all of our LSP statistics. We have all of the link utilization statistics. And we run a converged backbone. What do I mean by converged backbone? Essentially, we have all of our machine-to-user and machine-to-machine traffic running the same set of links and same topologies. So now, this path computation element can actually take all of this and build a demand mesh. And now it has the circuit DB to tell it what the desired state of the network is. and what my shared risk link groups are. So you can also do offline analysis. So once we actually have a demand and we have all of our health state of the network in terms of failure, everything, we can actually do some intelligent things across the network. How is the visualization of the solution end to end? This looks like a complex diagram, but it's not. It's basically just a walkthrough of what we did. We basically had a server that would talk into a bulk traffic manager through a bunch of APIs. The bulk traffic manager will essentially talk to the decision engine that's going to do its magic in the backbone and tell that, hey, you can transfer X amount of data. It could either be 100 Mbps, or it could be 75 gigs, whatever it is. One nice thing about this picture is you see this QoS bubbles that are there. What we did was, whenever we actually wanted to do a job transfer, we basically ensured that the host itself marks. So we don't need to actually have fancy ACLs or fancy policies in the routers that do QoS. So every job is given a forwarding class, which is essentially marked by the host itself before the transfer. What do you guys do on Facebook more often? You guys post status messages. You guys wish people happy birthday. Maybe tell people that you're fine during Hurricane Sandy and stuff. This is kind of what we see, or post pictures, right? It could be, so all we see is a collection of pictures, you can think. But actual data that we deal with is something like this. So we've kind of established that we have a lot of data that we deal with. So let's see what we are actually doing with all the systems that we have built together. So some of the use cases that we targeted with the differing elements that we built was these three. The first thing was what we called a durable demand. So we had application owners come to us and say, hey, can you quickly let me know if this can be done, and we want to transfer some data. So that is what we termed it as durable demand. So they come in, they ask for a demand, it goes through the same process of bulk TM, talking to backbone ensuring everything is fine, and then we go ahead and program it. The demand goes on, and once the job completes, the bulk traffic manager essentially informs the backbone PCE saying that it's done, and PCE removes that. The other aspect of it was calendaring. Remember earlier I had alluded to a little bit about graph search and Hadoop and so on. So what we found out was especially with graph search, that they needed to do this transfer of petabytes twice a week, and the SLA was supposed to be 36 hours. So this actually became calendared demands. So this automatically became inputs into our PCE. So every time before this demand started executing, we basically turned up a tunnel with the necessary bandwidth, and then it would just go on. So this was the second aspect of it, which was calendared demands. The final piece of the thing that we solved was periodic reoptimizations. So we talked a little bit earlier about binpacking. So then what we decided was, let's say we take the PCE and we start monitoring every single LSP in the network. Once it reaches a certain maximum threshold, if we can break that LSP into multiple sub-LSPs, then we can at least achieve a much better binpacking. It works the reverse way as well. We set a minimum threshold on each LSP, and once each LSP reaches this minimum threshold, then you can actually coalesce the LSP such that you can reduce the number of LSPs in your network. So let's see what happens, right? So we have a demand from East Coast to West Coast. It's fine. It's all been admitted. It's great. So we say, OK, go ahead. Voila, everything is fantastic, right, at this point of time. Remember I said we still run a converged backbone. So now what happens is there's a fiber cut. So at this point of time, we crash and burn. So this is why the importance of feedback comes in. So in actually the studies that we made, a 0.1% loss. 0.1% loss will actually cause 90% loss of throughput in TCP. Imagine that, a 0.1% packet loss. So we had to ensure that our feedback is tied into the whole system as well. So essentially, when we see this, PCE reacts. PCE basically does a recalculation and is able to inform the bulk traffic manager to either throttle or actually kill the job. This way, we are actually maximizing what happens in the network. So continuing the theme of posture, right? This is another one. At Facebook, we love to iterate. We love to ship products that can give us some gain. So let's look at the visible results that we saw with all this. So this was like a capacity graph that was before. Let's take a transfer and see what happened. So this was actually the allocated bandwidth for a transfer across time. This was the actual usage. So it's pretty close. So essentially what happens is the allocation and the allocation actually adapts itself to growing needs or decreasing needs of the source tier. This was fantastic for us. What else can we do? I talked a little bit earlier about our transport thing. Now imagine if you can actually extend this extend this PCE into multi-layers. So imagine you can actually have L1 and L3 and have a shared control plane. You can actually have standby transponders sitting there and doing L1 assisted bulk transfers. And you could actually have reconfigurable ROADMs. Imagine doing optical restoration in through software. To me personally, as a network engineer, this is an exciting time to work on because we are actually challenging the fundamentals that we have grown up with. We truly, truly believe that we are just scratching the surface and we are just beginning in this journey. And we have to continue to get to solutions that defy the norm to satisfy the demand and ever-changing landscape. If you'd like to talk to us more about our solutions or have different ideas for our problems, please seek us out in the hallway or catch us at the social that we're hosting tomorrow, and we can talk more about it. Thank you.
We have time for questions. Run, Matt.
Matt Petak, Yahoo here. One quick question. You said you've got your bulk traffic manager talking to all the servers. When it's doing the shaping on the server, is there any communication at the application layer to let the application know that it's being throttled? Or are you simply doing the throttling and letting the application deal with the aftermath there of the shaping?
Yeah, so I think the throttling is done by the TC mechanism in Linux, and then the application handles beyond that.
Okay, thank you.
Thank you.
Hi, Lockie, Lithium Technologies. Does your system support UDP and multicast traffic scheduling as well, or just TCP sockets?
No, we don't do multicast.
Okay.
Yeah.
UDP?
Yes. No, so it's essentially
yeah.
like TCP
Yeah.
for us a lot, but we actually don't do any of multicast in our backbone at all.
Okay. Okay, thank you.
So 2 questions, Vijay. The first question is, I would actually like to see the math where idle transponders actually work out in practice, because I've been trying to do that for like 15 years and I never managed to make the math work, so that would be very cool. The second component is, how do you do the network modeling for when you do your bandwidth allocation? So in the path changes, how do you construct and model the network for a priori traffic calculation and post facto capacity deletion model?
Sorry, I didn't quite get the second question. Can you repeat that, please?
The second question is, how do you do a representative model of the network for a priori traffic calculations, right? Because you have to have the topology. You have to annotate the edges and the links of the topology with available bandwidth, current utilization, and then put that into the path computation for allocation, right? So that's the first question. How do you represent that? And the second question is then, one post facto of capacity deletion, like say we have a fiber cut or something, how does that signal go back into the model, and how do you propagate that back up to the path control?
Okay. Regarding the first one, which is the standby transponders, so the point is to defy the odds, right? The point is to actually do things that the current technology allows us to do. So we have actually advances in the transport layer now where you can actually do software-based transponder shifting. How it works out, we'll iterate, we'll learn from it, and we'll see where it goes. On the second aspect of it, which is the path computation element, so we use a customized third-party solution for this. So in terms of so we have a demand mesh that it reads. It's able to construct this as a topology, and is able to know which traffic gets synced in a node, or which traffic actually is a transit through it, right? The other aspect that you talked about was like the network events and so on. So that is where we actually feed our extensive monitoring system. There is actually a listening, like a thrift-based API that the PCE listens to from the monitoring, which can actually feed the link failures. Then it goes ahead and basically does a recalculation. And similarly, there is an asynchronous notification back into our bulk traffic manager to say, hey, throttle this, or like go ahead and kill it.
All right, thank you. No, actually, my question was even more basic, right? How do you represent the model? What is your model representation inside your system? What you're talking about here are data feeds into the system, right? So for example, the TED is a data feed, but how do you represent the network model? That's something that we've been trying to kind of noodle around. You saw the talk today earlier about the Yang NetConf discussion. How is that implemented at Facebook?
Ultimately, it's a relational database that we represent all of this in.
Oh, okay. All right, thanks.
LJ, Cisco, can you comment a little on the methodology you used to get the, I think I heard the numbers right, a 0.1% loss translated to a 90% reduction in throughput? I'm interested in where those numbers came from.
So actually, there are, I think, some papers out there that describe this as well. So for us, what we did was we basically did like a brute force method, right? We said, okay, so we are actually going to see, we actually set up like these transfers, and we say, okay, let's start dropping packets on these, and come to a point where we actually think the throughput becomes, nominal. And we felt like, at 0.1% is where it was. So it's for us, it's internal study of what our patterns do. But from what I've heard, there are actually other research studies as well that kind of like, agree with what we have seen in the network.
Okay.
Any considerations about the traffic, vMotion within the traffic manager?
Can you self-identify?
Jay Fuentes, DTN.
Yeah. So we do not run any virtualized environment. For us, every tier or every host is a specific application. So we don't have to deal with VMs and stuff like that. So that's why there's no vMotion for us.
Mike Hughes. Early on, you showed your traffic packet size distribution histograms, and you said these are quite interesting. Why did you say these are quite interesting? Because I looked at them and went, I'm not surprised at all.
Okay, so these are quite interesting because we obviously, when we talk to vendors and we tell them that, hey, you have to support like 65% of 64-byte packet size at all the features that we want, they go back and be like, what, right? So interesting in the sense like, there's like performance associated with all of them. So it makes a big difference to like, as a hardware forwarding element and what features you turn on and the performance associated with it.
Ram Balakrishnan. Given the size of your network, is your traffic manager deployment is a hierarchical architecture, or is it centralized?
So the traffic manager is kind of hierarchical, is what I would say, but there is a global aggregator that is actually the arbiter to the whole thing. But essentially what happens is it kind of feeds into all of these, so we have like what we call a tier of hosts. And within the tier of hosts, you need not have everything talking the same way. That's why it's semi-hierarchical, but essentially you have the aggregator that's doing the most of the job here.
The second question is, did you say that you are throttling but host to host? Are you doing a path computational, capacity computational, path to path, capacity computational, and you're throttling at the host level?
Yeah, so what happens is the throttling actually happens at a job level. So for us, everything is a job, and everything boils down to a tier of hosts. So let's say a transfer actually is saying that I'm giving you an assured bandwidth of 100 Mbps. How it splits across the host is not necessarily that interesting to us. And then when actually this job aggregation becomes less than, say it moves from 100 to 50 Mbps, then the whole job gets throttled. So that's kind of like, it could be a bunch of hosts, but that's where it gets throttled.
So the last one that I have is, the QoS marking is done on every packet at the host level?
Yes.
Okay. All right, thanks.
Yeah, Clark Gaylord, Virginia Tech. So you're 0.1% creating 90% loss. Presumably that's because that's random loss as opposed to congestion-based loss. Is that correct? What kind of a link are you thinking is going to lose one packet in 1,000?
So, well, I think it's pretty subjective, right? In essence, like what we see in terms of like let's say we actually have like a cut. That actually tells us what services need to be protected as FRR. Where does the sub 50 millisecond come in as well? where we have hotspots, how hard do we have to run it, and so on. So to us, it was like more so from an understanding of what loss means to our applications and how we need to minimize it. That's kind of what it was.
Okay, last question, middle back.
Scott White, Google. I just wanted to clarify. So when you say 90%, you mean 90% throughput loss, right?
Yes.
Not 90% packet loss.
Yes.
Okay.
Yes. Thank you.
All right, we're getting ready to head out to afternoon break, sponsored by GoDaddy, NTT, and XKL. When we come back, we have a pair of submarine cable talks as well as a block of lightning talks. Thank you very much. See you soon.